Right, morning Year 12, just a real quick kind of basic ideas that you need to know your way around. We have the final section really that matters in this chapter that is going to go through every single piece of work. We are going to go pick up some stuff later. Obviously there's a lot to do with forces, but I'm just going to give you enough for survival aid to get through the big ideas. So a little bit of a Wile E. Coyote sketch for you for those that have got that kind of background in cartoons. But other than that, just going to have a look at this idea of resolving forces. Okay, so we've had a lesson on it. We had a bit of a chat on Wednesday about it. And this is using the same mathematics as up here, but actually conveniently turning this into a way of dealing with horrible diagonal things. So when we have pictures like the one I shared with you, they are often not neatly looking like that with the angle in here. They will be at different angles depending on how you're looking at it. Obviously it will depend on scenario to scenario. So the general idea is we have a diagonal force and we are going to resolve it, hence resolving vectors. We're going to break it down into that. Okay, so we're going to think about how much sideways it goes, think about how much vertically it goes. So you will need to come up with an idea, and this needs to be really clear when you're coming up with things. If you're describing stuff, we'll have a diagonal, and it will be diagonal at a certain angle, but a certain angle from where? So again, back to that idea, are we talking about north, south, east, west, or more usually something like from the horizontal? And we tend to do horizontal because don't have to, but the horizon is for everyone, so there may not be a vertical surface. So yeah, from the horizon is quite good. Now we think of it like that. Again, your data book, that will link in nicely. This is if it is horizontal and the angles from that, this is your x direction. So basically that's going to equal however much you're scaling it up, so however much that original force is, and you're going to multiply it by the cos of theta. Okay, so that's your key one. Most people will be happier with because it is adjacent. Okay, so really useful, and that means this second one is just the other one. So again, it's sine theta multiplied up by however big that original vector is. Okay, so this could be displacement, it could be direction, it could be velocities, it could be anything that has direction. Okay, field strength, magnets, etc, etc. So all of that links in. If I just take us into the next page, we're thinking about how to break down questions. Excuse me, can't get fat fingers doing it. There we go. So the idea is you may have something like this, and this has come up a few times with more on AQA. They really like these, but OCR use them a lot as well. They might have a wrecking ball on a yeah, we won't go into the Miley Cyrus, but a wrecking ball on a string, on a rope, and it is like that, where we have a force downwards, we have a force keeping it from swinging, some sort of rope, and then this tension here, so the string, this rope here or chain will have tension in as well. So I'll have two things under tension, and they want to know how big that is. Well, it's nice and straightforward if it's not moving, which means forces left and right are the same, forces up and down are the same. So if we split the diagonal into its components, horizontal bit of C, vertical bit of C, then it's much easier to actually find out the result by adding ones in straight line. So different directions, take CV and subtract B from it, and it will be a bit shorter, about that big. So that will be the resultant vertical bit. And likewise, A is bigger than C in the horizontal direction by that much. Okay, so you've literally just subtracted, like these are two tug of war teams at cross purposes. And then what we can do is turn that back into that diagonal there. Okay, and so the resulting force is that thing here. Okay, and that's how you do it. And then once you do that, to get the numbers, tan But if you know what R is, that's fine. You could use any of them, so you could do sine or cos or whatever your preferred trigonometric function is. But yeah, tan is just the two that you've already got because you've subtracted them, so it's a little bit quicker to do tan. And of course the length of it is Pythagoras, so the magnitude by Pythagoras. And all questions can be done like this. It's just that sometimes it may look that way or that way. And if I could just go back to that picture, literally, if you find it easier, then turn your picture around. You just need to think about where that triangle is, and more importantly, which is the right angle. So, crucial bit, if you have a force, then only a single force, which is being split up, then that will always be the big one. That will always be the hypotenuse because it is split into smaller components. Okay, so if you've got one force and you're splitting up, the force will always, one vector, then that vector will always be the biggest side of the triangle. So I keep saying forces because a lot of the questions are about forces, but not all of them. Not all of the vector questions are forces, but the vectors work in exactly the same way. So to get us through what you need for this topic, just to kind of give you that idea, basically all of the forces will add up. So if there is adding up and they add up to 0, then that object is not changing its motion. It's not changing in other ways. If they don't add up to 0, so there's a gap, then you have a resultant force. The resultant means that it must be moving, accelerating, changing shape, changing direction, etc. Okay, so for what we're doing, unless the object is in equilibrium, then forces cause change. And I'm going to put that in there. That's basically a sum up. If you've got a force, it's going to change something, motion, shape, direction, whatever. Don't just say it moves, for example. It's changing its movement. That's a really crucial thing to keep clear in your head. Okay, so again, other bits that are really important is that you need to be able to know your way around. So there's some forces, some of them are obvious, some are less obvious, even though they're everyday-ish ones. So again, just to kind of get your head around it, weight is always going to be there, so that force may not be drawn in diagrams, but there's always a down. If you've got an object, it is made of molecules, therefore they have mass, and therefore they have weight. And I will get everyone to keep putting this onto their arrow. I wouldn't bother writing weight. You might as well put the equation: mass times gravity, gravitational field strength. Okay, things are being pushed along. Doesn't matter too much what they're doing. So you might call this the motive force. Excuse me, start that again. Motive force, because it makes motion. Okay, or maybe thrust, or some other thing like that. That one's always a bit vague. The push. Don't put push because they're all pushes. Don't put push because they're all pushes. Sorry if you heard the alarm there. The thing that is trying to prevent it is friction, and friction is always in the opposite direction to what it's trying to do. So kind of obvious there. It's a contact force, so it's where the surfaces are in contact. Okay. But this one, for example, people might look at it and go, well, what's going on? Well, that is still friction. Why? Because if you put something on a slope, it's going to try and slide down the slope. And why? Because you've still got weight, okay? You've still got your mg. Because of that, a component of mg will be in that direction. So part of that weight being on a slope will try and drag it along the slope. Okay, some people will hold it onto the slope as well. Okay, but that bit's the force that's going to try and accelerate it down the slope, and because it's trying to move that way, the friction will be in the opposite direction. Okay, there can be times, and we'll leave it to the end of the year, where the friction's in the opposite direction. It takes a while to get your head around, so we'll not jump into that one yet. This one here, again, fairly obvious. Thrust, motive force, whatever. Drag. Drag or air resistance, if you like writing a lot more. It makes no difference in terms of mark schemes. You can write either, or, there we go. I should say up here, those are either or as well. So air resistance is not friction. Friction basically doesn't change. There's actually two types. It often takes a bit of a shove to start something moving, so that's called static friction. Then dynamic friction is once it's moving, and that does not change. That's basically constant, whereas air resistance isn't. And the reason is because you are bumping into air. There we go. And those air molecules, when you're driving faster, you're hitting more of them. So that doesn't take a genius to go, oh, the air resistance must be bigger, if you understand why that's happening. Okay, so hitting more air every second will give you more air resistance or drag. Okay, this one is one that catches people out because they're not really sure what the word is. You push down on something, there is a reaction. Again, you may have learned that, but stick away from that because we're actually after naming the force. Reaction is just general, like saying resultant. It's a general phrase. So that's your mg. This force pushing back, so the table or the surface pushing back on the box, that's called, it is a contact force, and it's known as the normal contact force, which I'm going to use in my diagrams as NCF, and mark schemes they use as NCF. Don't use it in exam board because they'll kind of go, what that could mean several things. But basically that means it's at 90 degrees to the surface. Normal just means perpendicular. Okay, so here conveniently we have normal forces. The ladder's pushing down on the ground is pushing back, normal contact force. Okay, the ladder is leaning against the wall, so the wall is pushing back. Again, it's at 90 degrees. Okay, so that's kind of crucial. Now, if you think about a ladder, what's it going to try and do? It's going to try and fall. So the bottom is trying to push out, so the thing that keeps it there is friction. Okay, pushing in the opposite direction to the motion, and I'll just put it there. And the top will slide down the wall. Okay, slide down like that. So again, friction is going to be keeping it up, or rather try to prevent it coming down. Okay, try to prevent it sliding along. Friction is always trying to stop you. Okay, you will get some maths questions like this. They've appeared a bit more, so we'll do this. You do it a lot in further maths, this kind of problem, further mechanics in further maths course. These have been around since millennia. I don't know when the invention of the frictionless wall came in, but that's been around for a long time because it makes it easier to do the maths. Okay, so we'll look at some of the problems like that in the next chapter about turning effects. So crucial kind of stuff there. The rest really is just kind of that basics. We have a few other forces, so again terminology. Again, we've got weight on both of those. What is the force upwards? Excuse me, get rid of the cartoon. The force that is making it float, whether it is actually floating or maybe just a bit lighter, it might be a rock on the bottom of a lake or a swimming pool, and it's lighter than it is in the air because of upthrust. Okay, it's not lift, it's not an active thing like an aeroplane. You are creating that force. This is just a force due to its volume. Okay, the water that wasn't there would have weight, so this is pushing up more again of that in a bit. Not in this chapter. So upthrust equals floaty force or buoyancy force. Americans call it buoyancy. Do not put this in the exam. Floaty force. All of you are ever so slightly lighter than if we sucked the air out of the room because you are slightly floating because of the air. You're more floaty in water because it's got more particles in the way, it's denser. Okay, and then one thing that really takes us into our next chapter, pairs of forces. Forces always come in pairs because things don't happen otherwise. Here we've got something that is stretching. Here we have something that is squashing or pressing. So these ones are known as compression forces. So you are squashing forces. So that's the phrase to use for that. We'll look at that with gases in year 13, but the maths is exactly the same as we're going to use in the next chapter, like with Hooke's law. This one here is tensile forces. And if you're thinking, where does that come from? Excuse me, let's just put that there. In other words, tension. Okay, so we use tension quite a lot. This object is under tension because the two pulling forces are stretching it. Okay, so those phrases are all really, really useful, really kind of crucial words to put in your answers, because it makes the examiner know you know what you're talking about. So get to use those phrases. I'll use them just to make it easier rather than saying push-pull, because all forces do that. And just again, something that we'll pick up on, but if you haven't heard the phrase before, equilibrium. Well, like I showed with that question the information a second ago, if the forces are all ending up so there is no resultant, okay, or excuse me, resultant equals 0, there is a resultant, but it adds up to 0. So if there is no gap in your triangle, or if there's 4 forces in your parallelogram, or whatever shape, pentagon of some variety, then this is in equilibrium. So if we go back to that phrase, that means nothing is changing. Okay, so it may be moving, it may not be moving, but it's not going to change its movement. Okay, so it's that change bit that's important. Really, really important. Okay, so again, another nice word to be able to slot in when we're talking about all the components of the forces adding up to nothing. Lastly, phrase to put in, free body diagram. Again, it's something. So here is Bob. It's always Bob in physics, I should say. So we have Bob on a ladder. He looks always like a nice, convenient round ball, because it's much easier to do that. And Bob on the ladder is producing forces. Forces on the ladder have changed because Bob is on it. They've not just got bigger, but they've actually changed direction and things like that. So it's all rather complicated, but actually, if everything is just staying still, then we can simplify that down to a free body diagram. So we can just think about the forces and slot them together into a parallelogram. So we can have that idea of all the forces clarified on Bob. Well, we've got the horizontal force, we've got the one pushing up on him like that. This is not to scale, I should quickly add, and that. So that's your free body diagram, which you can then change into a calculation triangle. Okay, so that's our crucial idea there. And again, equilibrium. Okay, not an equilibrium. Look close. They are all going tip to tail, tip to tail, tip to tail. These ones are going tip to tail, tip to tail, tip to tail, tip to tail. Not there. So that is your start. That is where they end up. And unfortunately, on my version, it's in a different colour. So this is your resultant. That's the difference that's left over. Okay, no gaps, gap. So you won't, to go to start to finish, that's your resultant vector. Okay, but again, if you prefer, if the question doesn't ask you whether to use a diagram or not, or rather, if it doesn't say use a diagram, then you might want to just use components, much easier. Okay, thanks very much, guys. That takes you right to the end of that chapter, which then means have good practice, loads and loads of slot questions in here, so shed loads of practice. They look quite big. You might want to do a bit of a sketch. Sorry, I'll say that again. Do a sketch so you can see clearly where the angles are. Always do a sketch. Often in the exams there will be a picture, but that doesn't mean a sketch. So have a look at mine if you're a bit stuck on how to kind of get started with them. And the phrasing will be, okay, which direction is that force? So that kind of stuff. And then there's some more at the back as well. So again, try using scale diagrams. I would suggest, if you've got graph paper, that's really useful, okay, because they're 2mm squares, which makes it easier to do. Okay, thanks very much, guys. Practice, practice, practice. You'll see these loads.